Okay, welcome all of you to session 14. We have two more classes to go. So let me show you what I want to cover today. These are the topics. I'm sure all of them are important topics in the processor architecture world. So I want to introduce these techniques and not to the very detailed level of how it is implemented, but at least I will show you the idea behind it so that later on you can read it and learn about all these things on your own. Okay. So register renaming. Let me explain what I mean by this renaming. All of you are doing it in your day-to-day life actually. If you see your official name and MAT is something, and on Instagram is something, and on Facebook there are many. You have many names on Facebook, but all these names refer to one person, that is you. So you give different names on different accounts for different audience. You give yourself different naming, you give it yourself. That is called renaming. You are renaming yourself. What your parents given you is this name. On Instagram or Facebook, you have many names you maintain for different purposes. Here we are going to discuss about how processor architecture does the same thing that you do inside the CPU. There are few registers which you know from R0 to R31 in ARM7 maybe. You know that these registers are there physically, and you can write assembly code accessing these registers. You can say R13, R14, R15, you can write. That means these registers are visible to you, visible to the programmer. It is when you say something is visible means you are able to access them, you are able to read into them, read from them or write into them, and you can see the value in them. They are called visible registers. Now, apart from these visible registers, CPU, based on the need, creates other set of registers, temporary registers. It's a hardware. It is in hardware like a register. It is also a hardware. It is all temporary registers. That means a temporary registers here can hold the value of R0 for some time. After that, it will be used for holding the value of R13 during the different cycle. So we create so many temporary registers which correspond to one of the visible registers at a particular point in time. So why do we need it? How do we use it? We will see that. But understand the concept. Register renaming means we are not making this R0 as something called RX. No, we are not renaming it in the sense. R0 is still R0 only. It is there in the same location. You can address it as R0, no issues. But we create other temporary registers which are named as for some time R0, some other times it is R31. So we create temporary registers to hold the values of our visible registers in the register set. That is called register renaming. It's a technique used for some purpose. Let us see what is the purpose. Data hazards, we saw that in pipeline as well as in the superscalar processor. Especially the scoreboarding we saw yesterday was not able to improve the performance of instruction execution. Though we have so many multiple units, because of data hazards, we were not able to make use of them. If you see the set of instructions, they were all adding up to some 54 cycles totally. And because of superscalar, how much we executed all of them, we took some around 62 cycles to execute all the instructions. This 54 plus some other cycles, if you add it, it will be equal to 66. Okay, totally these instructions would have taken 66 cycles, if they have gone through sequentially executed. But by superscalar, we are executing them in parallel, but still we only saved 4 cycles. We just saved only 4 cycles at the end of the day. The reason was that some instruction was not able to proceed further because there are some instruction which is trying to read from it, the same register. So we were waiting for that reading to happen, and that instruction was dependent on the div instruction, which was in the top div instruction, which took 40 cycles to complete. So effectively, till the div was completed, we were not able to do anything at all. So because of this, we were not able to make use of the superscalar architecture we built because of this data hazards. Can we do something so that the dependency on those data hazard is a dependency between multiple instructions? Can we localize the dependency between only set of instructions, and then the rest of the instruction can proceed further without waiting for the result or reading to happen from the previous instructions? Let me repeat. We have a dependency, but we want to localize the dependency. If you see in a particular city, if there is a traffic jam in a particular junction where 4 roads are joining, what do the police do? They reroute the traffic to some other road so that effect of this traffic jam doesn't impact the whole city. So they reroute it. They want to isolate the problem, isolate the issue. So here there is a dependency. We don't want the dependency to go on further down the instruction pipeline, not the pipeline, instruction sequence. We don't want that to go on affecting the further instructions. How do we do it? Let us see. Though there are many FUs, functional units, in the system, they were not used efficiently because of data hazard. We were not able to run them. Even if you have executed it, we were not able to write back the result. Because of that, we were not able to pump in another instruction. So either because of delay in the write back or in delay in reading the operands, we were not using the functional unit efficiently. Remember, functional unit is there. It can perform more operations, one after the other, of course. But once one operation is done, we want to use the functional unit for executing some other instruction. But we were not able to use it because write back was delayed, because it was some other instruction is still not read from the destination register, so we were waiting. Or we assigned one instruction, but operand was not ready, so we were not using the functional unit. So in some way, we were not using the functional unit at all properly. Register renaming is a technique to remove the data hazards so that instructions can dynamically be scheduled, executed in parallel using the FUs in the system. So we want to remove the data hazard by using this technique called register renaming. Register renaming is a mechanism in which a set of programmable registers are visible to programmer. These are all visible to programmers, which are all the registers that we use in the instructions, are mapped to program invisible registers. We are having hidden registers inside the CPU, which is not known to the outside world, outside the programmer. Programmer cannot access those registers directly. They don't have a name in them, name for them that you can use it in the instruction. You can still use only what is there in the register set, but we have many temporary registers which are internally used by the processor to execute the instructions. Remember, we have a register set which are visible to programmer, whereas invisible registers are created. That means I'm not saying that it will be magically, it will come into life. When you are building the chip, you already have decided that these many invisible registers are there. I'm not saying that it will be like a FPGA, you program it and then create the registers on the go. No, registers are there. Only thing is they are not visible, first of all, to the programmer, and mapping of some visible registers to them is dynamic. I can use one invisible register for R1 for some time. Later on, I may use it for R2. It depends on the usage. So that is what I call it as dynamically using it, but don't misread it that I am creating those registers from during the execution. No, it is all there physically. Some space is occupied by those registers, and we are using it dynamically. Okay, now I'll show you an example which we saw yesterday. Same example. Sorry, it is different. Okay, I'm not showing the same example. Little bit different. These three instructions are same. If you bother to look at the slides or look at the PPT or look at the video after the class, you may remember that these are the instructions which we saw yesterday. There was a dependency here, because of which this instruction was not able to proceed further. If you recall, I told you that cycles are like this. So div started executing, but it will end execution only after 40 cycles. Very, very long instruction. Now, because of this, it needs the result of that div. So this cannot proceed further. F6 cannot proceed because it is waiting for the result. So this is, now I will show you what all the instructions held up because of this. This is held up. I am putting an into saying that it is held up because it is waiting for the result of div. Now, because the implementation wants both the registers to be read together, it cannot read F8 also. Until F0 is ready, F8 is not going to be read. Remember, keep it in mind. Okay. Now, what about this store instruction? I am using it as a store instruction here. If you remember, store means it is storing a value from F6 to some other memory. This is also held up because F6 is not ready. F6 is going to be computed by this add instruction. Then only it can store it. So this instruction is also held up. What about this guy? This guy may execute the subtract operation because they are independent, assuming that I have another subtractor in the system. I have two F adder in the system. One is held by this add instruction. Another adder is used for subtract because there are two adders in the system I am showing you. So it can execute this instruction because the operands are free available. That means nobody is writing into it. So it doesn't have to wait for it. But the problem is the result is to be written into F8. Now F8 is to be read first before writing. So it cannot write into the F8. That means it cannot free up this FAD after performing the subtract operation. That means this is also held up. It is halfway through, but it is held up. Now, what about this guy? This guy also wants the value from F8, which is computed by this guy. When this instruction is held, this is naturally held. So, if you see that, because of this one guy taking 40 cycles and the dependency data hazards are there, none of the instructions are proceeding further at all. They are just, all of them are held up. Now, what is the use of having functional units and different implementation when you are not able to freely execute them because of the data dependency? That is data hazard. Now, let me throw up some quiz now to wake you up. Okay. So before that, let me explain only one thing. This dependency is what dependency? It is a read after write, because you have to read F naught. You means this add instruction should read F naught only after it has been written into by div d. So it's a read after hazard. Okay, you understood this hazard. I have a question now. Between add d and sd, this is a store instruction. This is the add instruction. If you see, both of them are having F6. I have colored it. I want you to identify what type of hazard it is. If at all there is a hazard, what type of hazard? You can also choose this if you say there is no hazard, or tell me whether it is a raw hazard, bar, or right after right. So let me, okay. Let me continue. Time is losing. We are losing time. Okay, so F6 is having raw dependency, which we saw. Now, what about F8? Now, this guy cannot write into F8 until this is read. That is also, it has to write after it is read. So it is not a raw hazard, it's a var hazard. Okay, it has to write right after read. Okay, so it's a var hazard. Now, is there any other hazard there? Of course, these two having hazard. Okay, and then even these two have an hazard. What is this? This is supposed to write into it only after this reading is done. Otherwise, store will store a wrong value. So write after read. So this is between these F6, these two instruction is a write after read hazard. And then between this F8 and F8, what is this? It should read this F8 only after this is writing. So it's a raw hazard. So I don't know whether you guys are all getting it. I want you to think about it, looking at set of instructions and see what are their hazards. Whether are you able to find out, whether are you getting confused between them. I can't explain anymore. I have explained it many number of times. So I'm losing time because of this. I'm not going to explain. I am going to tell you these are the hazards and I want you to understand it, because for people who understand it will be boring. Okay, I have to take care of them also. Okay, register renaming can be used to overcome this. Now I am saying I am going to use register renaming to remove. I see one thing is I'm not going to remove the hazard, but I am going to reduce the impact. As I told you in the traffic jam that is created in a particular junction cannot be removed, but I can at least try to minimize the impact of that on some other part of the city by rerouting them or doing something else, right? So that is what we are going to do now. So let me show you the same set of instructions. Now just analyze it, okay? Before even knowing what is register renaming, just analyze this. Always the impact of the data hazard between the instructions which are together cannot be avoided. I'll tell you, you cannot remove this by any means. You cannot remove this by any means. What I really want to say is, add D cannot continue with the execution until div D is completed. So even if I do any technique, I cannot remove it. That is there. Similarly, if these two instructions are there, I can't do much. It has to be written by this add instruction and I have to write into this. So the registers are the only way I can convey the information between this instruction and between a store instruction. You know that in a RISC architecture, I can only do arithmetic operation between registers, and I can also use only store or load to store it in the memory or read it from the memory. So effectively, I have to use one register here, I have to use one register, and it needs to be same. So can I do anything here is difficult. But look at the dependency that is created because of F8 being used here as well as here. See here, a new value is getting written into F8. Okay, it doesn't depend on this. It's called anti-dependence. Write after read is anti-dependence. Read after write, this is true dependence. So true dependence I cannot avoid, but anti-dependence I can do something. What is that something? Let me, if by now if you have got a clue, it's good. Why should I use F8? What is so, but compiler has generated this code using F8. Now, is this instruction dependent on this value? Is it dependent on anything coming from top? No. It is computing a fresh value here and then loading into this. And if it is not dependent on something coming from top, and if I am computing a new value, how does it matter whether I am using the same F8 or something else? Why can't I use some other register? Don't use this. Now, because I told you that register renaming is nothing but mapping some visible registers to invisible registers, internal registers. Assume I name them as S and T, some name. I am giving you some random name. Don't worry, there is nothing to, don't conclude that there is some meaning in it. Some alphabet. Imagine I removed this F8 from the instruction. Who is doing it? I can't do it in the instruction memory. It is CPU cannot, no, if it is trying to do that, it's you doing more job. It is not trying to do that. Instruction what is in the memory is same. It is still subd F8, F10, F14. What is the CPU reading is also same. Once the instruction has come into the CPU, I don't want to use F8 now. I see that CPU can understand this sequence. Hardware is able to think like a human being, and it is supposed to do it. Hardware is thinking and then trying to avoid the dependency. Now it knows that I am computing a new value. Why not I remove this F8 from this instruction and put some temporary register? I will allocate it. I will allocate this as a T. Suppose I have named all my temporary registers to A to Z. I can pick anything which is free and then say, hey, going forward, I'm going to assume instead of F8, this is going to be writing into T. Physically some register which is internal. I don't know. As a programmer, I don't even know it is happening. I don't have to know. As long as I give you the result, what you want, you don't have to know. So I change it to some value T. Now, it is not sufficient if I change it only here, because the next instruction depends on the value in F8, which is computed here. So what I should do, by now you should have guessed it, I should make this also T. Imagine the CPU is going into the register set, instructions after decoding and changing those register values. Instead of F8, it is going to use T going forward. Now, look at the advantage. Look at the advantage of this. This has become T. This guy has become T. Now imagine you rerun what would have happened in a scalar processor, superscalar processor. This is scheduled. Imagine the same scoreboarding, okay? It is scheduled, it is running, and I have a system. I'm sorry, okay, let me show you. I have two adders, I told you already, okay? I have two adders. So this add instruction is occupying one adder. I can allocate this sub to another adder, hardware adder. Now I can execute this instruction now. Okay, because this is not completed, 40 cycles are not over. This is held up, but this can proceed because that dependency of F8 is gone now. I don't have to wait till add D reads from F8. It will read. Add D will read from F8, no problem. I'm not disturbing it. I'm not changing the value in F8. Please remember, I'm not changing the value in F8. F8 is not disturbed at all. But I have introduced a new register, and this instruction is going to write into T, not into F8. So I don't have to worry about this instruction completing before even this starts executing. Before even this starts executing, it is going to happen because it is only taking 2 cycles, whereas fellow is taking 40 cycles. After that only ADD can even start executing. So if you see now, I have removed the dependency between this guys, especially this guy and this instruction. Now what have I gained? I have gained in the sense I can now start executing this instruction, which was held up because of F8. Now it's freed up. Okay. Because of T, I'm happy that I'm able to run it. Now what happens? This result is available. This result is already there. F10 is not disturbed. But the problem is, this is only 10 cycles, okay? So before even this completes, this fellow also can complete 10 cycles, it will complete. But now it wants to write into F6. Now I have a problem again. If I say I want to use F6 and this F6 are the same, I have a problem. What is the problem? Until store starts executing and reads the operand F6, I can't write into it. Now again I am getting into the same problem that I have. What is the problem? I cannot complete multi-D instruction because write back cannot be completed. I cannot write the result back into F6 because it is still held. I have to wait till this reading happens. So war hazard, write after read is happening. So again I get into the same problem. Now you are not restricted to use only one temporary register. I told you there are many. In fact, temporary register may be more than, it may not be more, but more, it depends on the implementation, more than the actual register set. I want to use one more temporary register. Let me call it as yes. Now tell me, where is the replacement I should now do? I want to use one more temporary register because I don't want this multi depend on this F6. Okay, I want to avoid that dependency. So that this 40 cycles of div-d only blocks these two instructions and nothing, at least for now, nothing below. I want to do that. That means I should do something. What should I do? Should I make this F6 as some temporary register? Yes. Or something else. Now, okay, I have a, okay, I found some problem now. Okay, I will explain that. Okay. Now, what I do, if I replace this with yes, okay. Here, what I am doing is, I am not mapping it to F6. Okay, let me explain what I mean by that. I am just removing this altogether. I even forget that F6 was used and then I'm using some yes. What happens? I am writing into yes the result and then storing it into memory. That's all. It is used only in these two places. Okay. And if you see this instruction, it is writing a new value into F6. So I can actually continue with F6 usage here, but do not use F6 in these two instructions. So there may be some confusion created because I am mapping the F6 to S. That means this also should become S. Okay. You might think like that. It depends on the implementation again. Okay. In my case here, in this particular case, I am trying to only localize these usages into, I'm even forgetting that F6 was used, and then I am temporary register, yes, I am putting. Okay. I will explain to you how does it help you. Now, the new value, whatever is computed, is written into yes, and that yes is stored in the memory. So this instruction can proceed further using F6 only. I'm not replacing this yes, using F6, or I may use something else. Okay. We'll right now assume that we are using F6 here, and it will proceed further. Why it is important that I should proceed further with F6? Because this value may be used below. Okay. Even if I am using F8 into T, here also I am replacing with a T. If there are other instructions which are using F8, I have to go down and change this also to T. Otherwise, I will have a wrong value. That you have to take care. So similar thing has to be done. Here I am not changing it, so I don't have to worry about it. Here, this is forgotten here with the S value. Okay. That means temporarily I am using it and then writing the result, then this is forgotten. We don't need to worry about it. Okay. So Now I'll show you. Because of this, what is that advantage we are gaining? We are gaining an advantage that because of devd, whatever is blocked is only these two instructions, and these two can proceed further. That is the advantage we have got. So this is the register naming advantage. Okay. So let me explain this. No var dependency between SD and multd because of this. SD is this, multd is this. We were having a var hazard. That means this was reading and then this was writing. It is removed. Okay, because of having yes. And then no var hazard between F8, between this and this. We have removed now. It is something else here and something else here. It's no longer F8 here. So we can continue further. No issues. So effectively, we have removed the, we have localized the block only with this, and then we are freeing up this thing. So what are the advantages? These instructions will be completed and new instructions can come in and they can occupy the multiplier or the adder and they can proceed further. Okay, till this divd is completed. After that, this will be completed. Okay, so note that raw dependency between add and sd. Okay, let me explain what I mean by that. Add and sd, these two, I replace it with yes. This doesn't mean that that dependency is gone. It is still there. Yes depends on this value. Okay, that dependency I cannot avoid it, but only thing is I have disconnected it from the rest of the instruction getting affected. That's all. Okay, I hope this is clear. Let me proceed further and explain you. You understand how instructions can proceed after register renaming. Try to run through the scoreboarding and see how you can run these instructions and how many cycles you will save compared to what we saw yesterday. Okay, so let me explain. We replace this F6 with S and then F8 with the T. So what do we gain? Instead of delaying the write, instead of delaying this write, we were delaying this write for this read to happen. Okay, this was having a old value and we were writing a new value. So let me read it. Instead of delaying the write until all the reads of by the previous instructions are completed, two copies of the location are maintained. Two copies. We maintain F8 and T. We have delinked them and it is going to have a different value. Okay, F8 is not going to be having the same value as T. T is going to have this added value, where F8 will have a previous value which was there, computed by the previous instructions. So we are delinking it. In fact, we have removed the dependency between them. So old value was in F8, new value is going to be in T. Okay, that is what I am saying. We are having two locations to have the copies of old and new values. The location could be both a register or memory. It's not that you have to find the temporary registers for only the registers inside the CPU. You can even do it for memory. Instead of going into the memory and reading it, you can keep it in the register. Okay, that I'm not talking about that implementation at all. Okay, and now let me try to explain this sentence. Reads done by add. Reads means I am talking about F8, reading from F8. Reads that precede the write. Sub D is writing into F8. You remember F8 was replaced with T. So reads preceding the write of the new value. New value is computed here in the program order. Program order, this is the new value, this is the old value. In the program order can be provided with the old value. Now reads from this instruction needs to be provided with the old value, which is in F8, even while other reads means multi-D. Multi-D is reading now. Multi-D is reading a new value. Other reads that follow the write provided with the new value. So if you understand this sentence, what I'm saying is you can still provide the old value to the instruction which are preceding the instruction which has given a new value, this also can read a, you can get a old value. Similarly, the instructions which are following this new value can be given this value for its reads. So you are not stopping this instruction as well as you are not stopping this instruction. Both are running. Now, because you introduce a new register, it is a new avatar, a new creation. Okay. So that dependency between F8 and this instruction is gone. We have given a new register to it. Okay. So the false dependency is broken and additional opportunities for out of order execution is created. Now, how are we creating the additional opportunity? We are allowing this to run. When you allow this to run, within 10 cycles, it is going to complete. We can allow some other mult operation to start. You see, this is taking 40 cycles. By the time 4 multiplier can be performed, all that we are gaining by doing one simple technique of register renaming. This is a beautiful concept which is an innovation in the CPU design, and I want to share it with you. You are going to come across this if you go for a master's degree or if you join a semiconductor company. You are going to see these kind of things in the real life scenario. Okay. So when all the reads needing the value, temporary registers have been satisfied. Okay, when all the needing the value, temporary, this word sentence I am not able to follow. Okay. Okay. So, okay, what I mean by that is all the reads, that means all the instructions. Okay. When I say reads means the instructions which are using them as an operand. They are using this temporary registers as an operand. I am calling them as all the reads. Suppose if I have another instruction called add, which is taking it from T, I'm saying this is one read and this is another read using the temporary register. So when all the reads needing the value in temporary registers have been satisfied, the temporary registers created can be discarded. Once you, okay, when all the reads are satisfied, suppose it's what I mean by that is when will I discard it? Okay, let me explain. This instruction needs the read value which has come from here, right? Now, after the store instruction has read from the S, do I need S to be preserved? No need. That's why I'm saying that I am replacing this with S, but I'm continuing with F6. I don't need to maintain S no longer after these two instructions are done. That is what I'm saying here. That temporary registers can be discarded. What I mean by discarded means this temporary register S can now be used for mapping or instead of some other register, I can use it for something else. Okay, something like that. I can use this S for some other instruction. I can use it for some other removing some other data dependencies. So remember one thing, there is no maintaining the link. Okay, a processor is not going to remember there was F8 earlier, F8 earlier. Okay, it doesn't remember. Similarly, it doesn't remember F6 was there. It doesn't have to save this value in S back to F6. No, there is no guarantee. There is no need. F6 is having something else now. So S can be discarded as soon as their usage is done. It was required only for these two instructions and it is taken care of. So why are we doing all this? We are doing it because all these instructions are executed out of sequence and we want to execute as many instructions as possible in parallel. If you want to do that, the dependencies created by these data hazards have to be handled. You cannot remove it, but you have to handle. How do you handle them? You put them with different registers so that it is localized. See, the dependency between this P is still there. I'm not removing the hazard. I am only removing the hazard getting percolated or getting affecting many instructions. I do not want the hazards to impact instructions which are farther away from me. Can I remove the dependency somewhere, disconnect them, and try to have the remove the impact of this dependencies on this instruction? That's all. We have removed the dependency which was there between these two is removed. One data hazard is removed, but some things will still be there. Okay, let me explain this. This data hazard was there earlier. I have removed it. So I removed one data hazard by replacing it with F8 with a T, so that the impact of this on instructions below is removed. Okay, so it's like cutting off something. Okay, I hope register renaming is understood by you. Now I will tell you how it is implemented only in one slide. I'm not going to go into the details of this because it will take another class, which I don't have now. Now, these temporary registers are in the reservation stations. Okay, it's called reservation stations. They are a set of registers holding operands and results of every instruction which is being executed by the functional units. So actual register set is here. FP register set is here. Instructions are coming in from the memory. Okay, and there are two interfaces to the memory. Data memory. This is instruction memory. This is data memory. One is for loading the data from the memory. Another one is storing the data into the memory. So effectively, I have these interfaces to the outside world. This is for reading in the instructions from the instruction memory. This is to, if I do a load operation, those from the memory, data memory, I get the values on these buffers. If I do store, I store it from this buffer into the memory, data memory. So if you see now, compared to what you saw in the CPU design earlier or in the pipeline, the values to the memory are not directly going from the register. It is stored in a buffer and then given. Similarly, what is coming in is stored in the buffer and then coming into the CPU. So there are some storage spaces, lots of temporary registers. Now, even to the functional unit, they are not reading the operands directly from the register set. They are not reading it directly. I told you sometime back, last week, that functional units are separated little bit away from the register set. It is happening here. They are not reading the operands directly. They have buffers. Now, I have an option now, either keep this value here and then continue to have it, or I create this as a temporary registers, renaming it. Now, if I have two instructions, as I told you, let me explain these two instructions and these two instructions. They are using from S. They are also using from T. These S and T, where will they be in the structure? Add instruction. Add instruction is supposed to be done by FP adder. So that instruction is coming here before getting executed. This instruction is coming into this queue, and S is created now. Okay, S is created here, somewhere here. Okay, I am not using any F6 which was there from here. I am not using it because I am only writing into this S. I don't need to read the F6 at all. So it is used by this. Yes. Now what happens after this execution happens? Execution is done. It is going here and coming back here and writing into this. S value is written. It is not even going here. S is written. Now store instruction. Store instruction has to go through this buffer. It has to read S value to send it out to the memory. Now this SD instruction, which may be running somewhere in the load store functional unit, I'm not showing everything. It will not read from F6 which was there. It will read from this value. Okay. See, it is reading from the local register, temporary register. That's why you see that all these things are connected. So I can actually perform a read from here. This guy can read from there. They have a common bus and then they read it. This is a common data bus. They use it to read from these registers. So this instruction can read from the temporary value register which is created here. Similarly, when sub D is executing, suppose it is from the same FP adder, it may be different, okay, in our case. T is created, in the sense I am allocating this space for T. Now multiplier is executing this multi-D and it wants T. It will take from this register here. So it doesn't have to go to a register set at all. So this is how it is implemented. Now I'm not going to spend time on this. Self-learning exercise, not before the exam. I'm not going to ask you questions from this section. Now by now I am seeing in your mind, okay, I don't have to read it. Please don't read it for an exam. I want you to do it after the exam. Read this section, understand this scheme which is called Tomasulo scheme. It's called Tomasulo scheme, which is using temporary registers which are called register renaming, and it is using common data bus and the reservation stations to do the dynamic instruction scheduling. So what is this scheme? This is the next level of scoreboarding. Scoreboarding doesn't have these features. Register renaming is not supported there. In scoreboarding, it was reading directly from the register set, whereas in Tomasulo scheme, it is reading from temporary locations, which are register renaming, nothing but register renaming, from reservation stations, and they exchange the data using common data bus. So it's very interesting. This is what is being implemented in all the superscalar processors that you see in the market, maybe much more than this, but understanding this will help you know what is done inside a processor. How, whatever you write, whatever program you write, now you will remember for sure the instruction that you see, the assembly instruction that you generate in system programming. I told you, you can create a .s file from your C file, right? Assembly listing you can create with a .s file, .asm or .s with a -s option in GNU compiler. You will generate the listing of assembly instructions. They give you the list of assembly instruction like this, but remember one thing, they are not executed in the sequence you are seeing them. They are executed out of sequence by all the processors that you have in the laptops or servers, where whatever is being used now. Maybe embedded systems are different. They may not do these kind of things, most of them. I'm talking about all the enterprise servers and other laptops. They all do superscalar in the processor. So keep it in mind. It will help you in interviews or in your later studies. Okay, I'm going to now give a break after this slide. I want you to compare what I showed you just now, which is the Tomasulo's algorithm running on that structure, architecture, versus what you saw yesterday, scoreboarding. Hope you understood this. I am going to give you a difference between these two. God help you. It shares many ideas with scoreboarding. This is also similar to scoreboarding. It combines the key elements of scoreboarding scheme with register renaming. So it is combining what I showed you yesterday and what I explained you just now, which is renaming. Both are used in Tomasulo's scheme. The algorithm which is used by the hardware is called Tomasulo's algorithm, and which is nothing but a dynamic instruction scheduling scheme implementing not only what was done by scoreboarding, also register renaming. That means it changes the registers, renames them based on the dependency. It's not arbitrarily going to change it. Only if there is a dependency, it wants to cut off something, it will do it. Register renaming is achieved with the help of reservation stations, I told you, which are nothing but the buffer, the operands of instructions waiting to be executed. So the instructions are waiting for the FU to execute it. There is a buffer which is called reservation station. They are all waiting, instructions are waiting with along with the operands for FU to take it one by one and start executing. Hazard detection and execution control functionalities are distributed. Now, if you recall, I told that scoreboarding is centralized, whereas Tomasulo's algorithm or the scheme is distributed. It is not in one place. The intelligence of finding out the hazard and then exchanging information, renaming the registers are not in one place. It is distributed over different hardware in the same system. Okay, don't think that distributed means it is in one computer on another country. Okay, it's in the same CPU, but it's all handled by different circuitry in the system. Results are directly passed to functional units from reservation station. So results are passed, even operands are passed from the reservation station rather than from register set. I told you that also when I was explaining the Tomasulo scheme. So that's all. I hope you understood this. Now I have a question. Should I break now or later? So how do I cannot start a polling. You can put a thumbs up for continuing. If I don't see any thumbs up, I will not continue. That means I will come back, but I won't. I will give a break now. So I don't see anything here. I don't see anything here. People are scared of even giving thumbs up. There is one, Nila. Okay, I am going to play some song for Nila. Nila means moon in, oh, 1 second. Wait a minute. It's not going. So today we will cover two more concepts. One is reorder buffer and speculative execution. Okay. Now, what is reordering? When you reorder something, you are actually disturbing the order. Okay. If suppose I give you a set of numbers 1, 2, 3, 4, 5, and then I tell you to reorder it, you will do it 5, 3, 2, 1. Okay, something like that. Now, the name says it is reorder buffer. Actually, it is what is it doing is it's ordering it. Okay, I'll tell you why it's called reorder once I explain to you where it is used and how it is used. Okay, so now let us see the implications and then come to this. When instructions execute in parallel on multiple FUs, the ROB is called reorder buffer, serves the function of bringing completed instructions back into an order which is consistent with the program order. So let me explain. We started off with a sequence of instructions in a basic block. That means what? Between this jump instruction, there are some set of instructions which are to be executed in the same sequence. They came into the system in the IF stage. It got decoded and then they got issued into different functional units in order. This is in order. Everything, whatever we are seeing is in order. they got issued, but they started executing out of order. Why? Because some instructions was waiting for some operand, some was waiting for the functional unit. So there are so many reasons, okay? And some functional units do it in one cycle, some take 40 cycles, some take 20 cycles. You can imagine, you know that. So imagine if I had a instruction div, load, multiply, add, subtract, everything is one after the other. They're all issued in order, they're all getting executed in order, but they complete execution out of order. Out of order because they are taking different cycles. Now what is happening? I told you that programmer wanted to do something and they have provided the instructions in the sequence. Our CPU sitting in between is executing it in some sequence based on its convenience, but it is taking care that there are no data hazards, so that the functional units are getting proper operands and they execute them. Okay, execution is done. Now it is properly done because data hazards are taken care of. Operands are correct. But the problem is they are completing it out of order. They are completing the execution not in the same sequence. Something started earlier will end later. Something started later will finish early. Now what is happening? We are getting instructions getting completed in a out of sequence, not in the same order they are completed. They are completed in a random fashion, totally in order. Totally out of order. Now, is it okay if I write back those results into the register set without bothering about the sequence? I cannot do it. When I am writing back the results into the register set, because execution only is completed here. Remember the pipeline, execution is only completed. Write back has not been done. Writing into the register set is not done. Now you have an opportunity to do something innovative that you avoid the hazards created by the write back that we saw earlier. Because write back has to be done into some register set, we were holding on to some instructions earlier. Now suppose, similar to the register renaming that we followed while data hazards are removed, can I do something similar to that in the write back stage? What I want to do is, if I have instructions which are getting completed out of sequence, I don't bother to write into the destination registers immediately, but I cannot lose the value that has been computed. Suppose some addition was performed, I have the result, but I am not writing into the destination register immediately, because I want the previous one to be completed before I write the result. Now what I do, these are the instructions. What I do is the instruction issue itself, I do it from ROB. ROB is nothing but a buffer, a cyclic buffer. The instruction when I am issuing, imagine I write into the ROB first, all the instructions, okay? All the instructions I write into the ROB, which is nothing but a cyclic buffer. That means I know where is the head and where is the maximum I can write. So I keep writing into those buffer the instructions, what instruction it is, add, mul, whatever. And then I also keep track of which are the operands and where is the destination, which register the destination. Actually, operand also is not needed. I'm sorry. Operands are taken care of by the other units, reservation stations and other things. ROB, I don't have to worry about operands. Only thing what I should worry is where is the result computed is supposed to go, which register it is supposed to go. Suppose if I maintain for every instruction the value computed and to which register it is supposed to be written into. Suppose value computed is something R1. This is the value computed by this instruction, add instruction, but it is supposed to write the result into R0. This is the value computed by multiplier unit, and the result should go to R13. I need to keep the value, what was computed, and where is it supposed to go. But I am not writing into those registers. I am not writing into that. I am keeping it in the temporary buffer. But I am remembering the order in which the instructions were issued. I told you issue is happening in the same order as this program. So I store the instructions in the same order in the cyclic buffer. Why is the cyclic buffer? It will go back and then keep going it. Okay. So I can have at a time, suppose if it is a 10, depth of this buffer is 10, I can have 10 instructions in execution in the same sequence. Now, assume that this first time ROB is there. First instruction which came in will be here, and it is getting executed here, and the result will also be here, and which register it is supposed to go will also be here. So I keep holding these values and the destination registers in the ROB. I will commit those values. Commit means writing into the register, write back. I do it only when I have, if suppose this is the first instruction, without this result getting written into the register set, I will not write the next one. When I have two things ready, I write it. Suppose this is still pending, things are ready, I don't write it because this is pending. I will wait. Once this functional unit completes and puts the result, I write all of them. Do you understand? I go in the same sequence, I write the results back. If one of the instructions is holding, I just don't write those results, but I accumulate them. I'm delaying the writing of the results into the write back mode, into the destination registers, till all the results of the previous instructions are ready. I hold it till that point. If the previous instruction result is ready, I go start writing everything one by one in the same sequence they have executed. So what I am guaranteeing, the original intended program order is assured. That means the functionality is not affected. At the same time, I am allowing more instructions to be in execution. I will not wait for the write back result for holding some register, some functional unit. I don't do it. As far as this unit is concerned, execute unit is concerned, once it has written the result into the ROV, it doesn't have to worry whether that value is really written into the register or not. In that case, if it is not written into the destination register and some other instruction in the down the pipeline wants that value, it will take it from ROB. It will not go to the register set. Remember, we were having reservation stations to hold the values. We are not actually, reading from the register set, we are holding it. Similarly, writing also we are holding it. We are not writing into the register set immediately. We are waiting for other instructions to complete. We are holding it in the immediate temporary buffer. This is called ROB. So if any instruction down the line wants the results of computed by the previous instruction, but it is not yet written into the register set, no problem. I have it in the ROB. I take it from there. I don't go to the register set at all. These instructions take the values from this ROB. So correctness is assured, and there are no data hazards because of write back stage. We will not hold this writing back of the result. Earlier what we were doing, if suppose some functional unit is supposed to write the result, it is not able to write it because of the previous instruction. This unit was waiting. I have to write the result, please, I am waiting. That will not happen. Once it is written into ROB, this functional unit is free to take the next instruction because the results are saved somewhere. It is not with the functional unit anymore. They are in the ROB. This is the crux of this logic. I hope this is clear. Let me explain it now with a slide. Note that instructions may complete in an order, not in order, in an order which is not related to program order, because instructions are issued in order, but they are not starting in the same order because some may be waiting for the operand. Because of that, they may not start immediately. Even if they start, they will not complete synchronously because each functional unit is going to take different amount of time. So the completion of execution of instructions from the functional unit is not in the same order in which the program came in. They are out of order, but they need to be committed to registers or memory in the program order. We have to write into them in the same order in which this instruction came. Then only it will look similar to what the programmer wanted. So how do I do it? I keep it in the temporary buffer. So this out of order completion results here. This is the result, but I need to write it in order. This is what I want. This is the outcome from the FU, but this is what my intent is. ROB does this conversion. ROB helps in writing back the results in order, though the completion happened out of order. So what happens? It will be held in the ROB. It will be waiting in the ROB so that the results are written into the register set in the original order. Till then it will wait. Now remember, the waiting is not gone. Waiting for writing into the register set is not gone. But we are saving time because of freeing up the functional unit. Earlier, functional unit was holding the result and waiting. I want to execute next instruction, but I cannot do because I have to write this result into the register and there is a hazard, so I have to wait. Now that is gone. I can write into ROB temporarily so that functional unit is freed up to take the next instruction. See, everything we do here to make sure the functional units execute as many instructions as possible. We want to use this hardware effectively, efficiently. Because of the data hazard, all these issues are happening. We cannot avoid it. You cannot tell the programmer, don't use the values of what you computed earlier. Then they will throw your computer out of the window. They have to use what they compute. But the thing is, we are satisfying the programmer's interest, so taking care of their interest. At the same time, we are keeping our CPU busy doing some work. Whose work? It is a programmer's work. But we are doing something extra hardware we added so that we store the results temporarily in the buffer before writing into the register set so that user does not see the correctness is disturbed or there is a fault in it, but CPU can now use the functional unit effectively. So at any time, program state or processor state, remember one thing, if you recall in the OS course, I told you when the processors do a context switch, I never mentioned about ROB, reservation station, instruction buffer, store buffer, write buffer, all that I didn't talk about. I said the status is in the register set. So the register set is the master copy that only shows the state of the processor or the state of the process running in the processor. So when there is a context switch, we need to do pending jobs, whatever is there, to the level possible. If it is not possible, you just flush the ROBs. Don't bother. We will run them later on. We will execute them again. Context switch happens by saving the state of the register set only. It doesn't copy all the reservation stations values, all the ROB values. It doesn't save. It saves only what is in the processor register set. So a state of the program or a process is nothing but the register set. What is the content of them? So at any time, program state or processor state are defined in terms of instructions which have been committed. That means which have been written into the register set. Their results are reflected in appropriate registers and or memory locations. So only committed instructions are considered to be done. Other things are all we are doing it ahead. But we are not going to save it. Let me give an example. All you guys, those who are did the systems programming or some other course, all of you are ready with for the exam. Another 2 days, I am going to crack the exam. You are ready, but there is a context switch happened. COVID context switch. All of you are asked to stop whatever you are doing. No exam now. Go back home. What happened? You cannot say that I have prepared. I am ready now. I want to write the exam. No. You are taken out of the CPU. What has been done? What exams you have written so far, which are on the paper, which is similar to register set, is only taken. Context switches happened. You were ready for other exams in the pipeline, but you are not now. You cannot say those things the college should take. No, gone. You have to come again, write those exams, do whatever preparation. Hope you remember all that what you studied. I don't remember what I thought. So let us see. It will be fun when the program starts, when the exam starts. So what will happen is these incomplete instructions which are there, which was actually executed and ready to be committed, are will be run again. It will be executed again because there is no way their results are not captured there. It is halfway through, so nothing can be done. So actual state is only the what is in the register set. The concept of program state or processor state are important in supporting context switches. I told you when I do a context switch, what do you do? We copy all the register contents of this process into the PCB, process control block, and then bring another process into the CPU, copying the register set what was there when the context switch happened. That values are copied into register set. Then the PC program counter starts executing it. So when it executes those instructions, it will be from the time the committed instructions were there. Whatever was executed after the committed instruction, CPU might have executed much more than what was committed. They will be rerun. They will be executed again after the context switch happens and the process comes back to the CPU. So that is one concept you should remember. What is, you should be able to relate what you taught, what you learned in OS and this. I am not changing anything that I taught you. Processor state is still the register set only. Though we have so many register renaming business, and then we have ROB, all of them are there, but still we are not going to save all these things because they are all not visible to the programmer. When I say it is not visible to the programmer, most of the time it is not visible to OS also. Remember, OS is also a software running from the memory. It has some control on some registers. It's in the kernel mode. It can change some memory management unit and all that. But still that fellow is outside. As far as these reservation stations ROB are concerned, it is still very private to the CPU implementation. So OS does not have to know, or it is not required to know, these are all the intricate implementation details of the processor. That is what Intel and AMDs are doing. Windows guys, Microsoft guys need not have to know. They do not share that information also sometimes. They will tell something, but it is all invisible. Once I say invisible to the programmer, it is true for system programmers also who write the OS code. So OS fellows also write the code only to save the register set and restore the register set. They keep those copies in their process control block, but not this ROBs and other things. It is impossible to save all of them. If you start saving all these things, you will never do a context switch. Context switch has to happen in the shortest duration, I told you. Okay. Now what about this precise exception? Let me explain this little bit now because I am not going to cover it later on. What is exception? Exception is something which happens because of an instruction being executed. Let me give an example. Div instruction is getting executed with the two operands. Div instruction, it is executed. Imagine there was a sub instruction, there was some load instruction, something below. And we are imagining a scalar, super scalar processor. Divider is doing it. For 40 cycle, this fellow is going to take the division job. By then, subtract is done, load is done, this is done, and sometimes it is maybe even committed. Committed means it is written into the register. Now, I am saying it is not going to be written into register, it is going to be written into ROB. Okay. Now we learned ROB, so I can say that it is not going to be committed, it is going to be in ROB. That means what? These results, what was computed by these instructions, have not gone to the register set. Let me show you the register set here. This result is computed, it is supposed to go to R1, but R1 is not going to have this value. It is only stored here, saying that a subtract instruction was executed, it found out some value V1 and it is supposed to go to R1. It is in ROB. Why it is not committed? Prior to this instruction, div D was there. Div D or div. It is not yet over, so I cannot commit it. So ROB does not write the result into R1. So R1 is not affected yet. Imagine an exception happen. What is the exception? Exception is the abnormal situation happening because of executing an instruction. Now, what is the abnormal situation can you get in a div instruction? All of you should be able to tell me the answer is a divide by zero error. It is one of the possibilities, divide by zero error. Based on the operand, I may get a divide by zero error. Now, imagine a situation that div was waiting for one of the operands, so it was not executing at all. Sub executed, this executed, this executed, all of them are in ROB. They are putting the results in ROB. Now, this guy got an operand. One happens to be a zero. So when it performs the execution of this operation, it is going to raise an exception saying that, hey, I got a div by zero, divide by zero error I got. It is not supposed to happen, it happened. Processor will be interrupted. Exception will be, exception ISR, exception service routine will be executed. Now, when the CPU generates an exception, imagine you are running a debugger and then you are seeing the register contents. Okay, you are running a debugger and then suddenly the debugger says that your hardware raised a div zero exception and it is freezing it. It is stopping the execution and then showing you the register contents. It is showing you all the register contents. If you remember in Arduino class, we saw register content on the Arduino Studio, right? So Atmel Studio, sorry. What will it show? It will show the register content of these instructions. Whatever it has stored, it should show only those values. It cannot show the newly computed R1 value because one reason, it is still in ROB only. It has not gone to R1, so it cannot show. So if I have a system like ROB, okay, I don't have to worry about committing the results of this instruction into the register set like we were doing it. I showed you that it was committing it. It was not precise. Okay, precise exception. Imprecise. It was imprecise exception. That means if I don't have a ROB, what I would have done, if subtract was completed prior to division, R1 was written, I would have written the result into R1. Now, if the exception happens in div, R1 is not going to have the value what it was supposed to have. Prior to the execution of div, whatever was the value of R1, that should have been there in the R1, not the value which was computed after the division. If it is there, it's called imprecise. The exceptions are imprecise, not precise. But we don't accept it. We don't want that kind of a behavior. We want a precise exceptions to be supported by the processor. How can you achieve it? If you have a ROB, reorder buffer, this subtract result wouldn't have been written into R1. It will be available only in ROB. In that case, this R1 is going to have the value which was there prior to this execution. So if div was not completed, it stopped in between. I will still have the value which was originally there in R1. So I can support precise exception. I hope this is clear. I am not going to explain more. You have to rerun this video if you want to understand it. But I will ask question because I spent some minutes here explaining it. Let me summarize. Once I tell this, some guys will start listening now. Let me summarize. I don't know whether you can understand this. Some instruction is there. Div instruction. It is starting the execution delayed because of some data hazard or whatever. Other instructions which were there next to below them were completed because of superscalar. And I have an ROB so that the results computed by this are not written into the register set. Instead, it is preserved here. Later, it will be written into register set. In the same sequence, the instructions are completed. If I store the intermediate results in ROB, then if this div is starting late and then gets into an exception, that means it got into some divide by zero error. Because of that, it cannot continue the execution. It should bring it to the notice of the programmer, creating an exception to the CPU, and CPU will run an exception handler. Now that handler will do something, repair work, and then continue the execution. Now when the handler is given a control, it may decide to stop the execution and then give an interrupt or some debugger. If you are debugging it, it may show you on the debugger that this is where the instruction stopped. Now when the instruction stopped because of div instruction, I should have the register values which are computed by the instructions prior to the div and not later to div. If I have a ROB, these results will be written into ROB and not into register set. So I will have the same value, correct value, which was there prior to div, because I have not committed it now. It's not committed. Now you may wonder, what if this instruction itself is not committed? Suppose for some reason this is not committed, then you will have a problem. No, if it is in ROB, you should write it and then only create this exception. This previous instruction should have been committed. Okay. Otherwise, imprecise exception may come. Assume that before div all the instructions are committed, and because div is taking more time, I am not able to commit these instructions. That means they are all executed, results are found, they are all available in ROB, but not written into register set. In that case, if the exception happens, I will be able to show the register values as if nothing was done after this div, though a lot of things have happened after div. All those things what I did is all available in ROB, but nothing can be done. Exception is created, now all these are all gone. This is flushed. Remember, when an interrupt or exception happen, a new set of instructions have to be executed because the handler has to be executed. In that case, new set of instruction will come into the CPU. Remember, this old state, what is there in ROB, is all gone. Now, handler is going to come. A lot of instructions are going to be executed for the handler by the same CPU. So you cannot keep these values and then come back and then start again. Like what you guys have to do now, after you come back, you have to write the exam completely. Okay. So the exception has happened, all is disturbed. Okay. So similar thing will happen in the CPU. All the intermediate things what you did is all gone. Now we have to start afresh. If you are able to do this, then it's called precise exception support or imprecise. If it is not possible and you are committing some results of the next instruction into the register set, then you are disturbing it. You are not showing the register value exactly same as what would have been before the exception. Okay. So I hope this is clear. I'm not going to explain again. This is what is the example that you can see it. I have already explained it. So what I'm saying here is, suppose this div is taking more time if I am committing this, it will be in ROB. So if this is generating an exception, all that done after this div is forgotten. Only what is above is maintained in the register set. These are all in ROB. Results are in ROB. They're all gone. Okay. That's what I'm trying to say. What is precise exception? Okay. Now, let me explain what is ROB. ROB is a cyclic buffer holding instructions in the program order. The instructions are issued to relevant FUs from ROB. Okay. Instructions are as they come in, because remember, when you are getting the instruction only, you know the order in which they are coming. If you don't catch it during that time, you will lose the order, because you cannot catch up, you cannot reconstruct the order of the instruction once you do not capture it when they come in. So when the instructions come in, it is stored in ROB. Okay, it is not that when the results are out, because when the results are out, they are out of order. So when it is coming in order, you store it in ROB. Okay, since the instructions do not necessarily complete in program order, they don't complete in program order, the flag with each ROB entry, each ROB entry is one instruction, and each of those entries will have a flag to indicate whether the instruction in that position has been completed or not. If you have an entry in the ROB, it shows you the order in which the instructions came in, and it could be completed, it could have been completed, or it is still being executed in the functional unit, or it is not even started, it is waiting for the operand. It could be any state, any stage it will be. So there will be an entry, a flag entry to say whether it is completed or not. Okay, let me show you now. Instruction I is here, I plus 1 is here, I plus 2, I plus 3, I plus 4, I plus 5, I plus 6. So these instructions have come in. They are all, maybe one is adder, one is multiply, one is divider operation, one is load, one is store. They are all in different stages of execution, or maybe this is completed, this is completed, this is still pending. Anything can be there. So you are just storing it in the order in which the instructions came in. Actual instruction, it depends on what you store. And then the value, which is the value, it's not an operand value, the computed value, and where it is supposed to be written into, which register value it is supposed to be written into. Suppose, let me give an example. I have an instruction, add F1, F2, F3. I'm not storing this F2, F3 anywhere. Okay. I am storing the instruction that add F1, F2, F3 came in. I am in some way, I am storing that this is the instruction. And what is the value computed? I am storing not the actual content of F2 and F3, the result computed. That means if I have an entry here, that means it is already executed. Okay. The value computed is not gone into F1, it is available here. And then I should know where it is supposed to be written when I want to write. So I will say that F1. Remember here, it is not storing the value currently in F1. It is not storing the value of F1. It is only saying it is the F1 register. F1 register, floating point register, F1. And ready means if it is this value is there already, that means it is computed, then this flag will be true. What I mean by having an entry called true here, that means this instruction is completed now. And this is the topmost instruction in my ROB. These are the last instruction and this is the topmost instruction. There are 8 entries in the buffer. That means what? I can safely write this value into this F1. I can write this value. This value I can write into F1 and remove the entry from here. Now what happens? Another instruction can be put into the instruction buffer ROB, which is I plus 8. I plus 8 can come now. Now remember, this ROB can hold only 8 instructions, suppose. Then I can have maximum of 8 instructions issued. I cannot issue an instruction to any functional unit unless I create or make an entry in the table. Because if I don't do it, if I don't maintain it, I will lose the instruction in which order it came. It is like this. When you come into the class, you have to make sure that you log into the Zoom and then register yourself that you are the roll number and you are come into the class. You may even ask your friend to switch on the mobile, and if you are so much keen, you can switch on the mobile and video and then keep listening to this from his mobile. But that will not be considered that you are attended the Zoom class because you are not registered in ROB or in the registered thing. So you have to join Zoom to register yourself. Similarly, these instructions can execute without even getting the entry here. But the problem is you will not know in which order it came and where I am supposed to write the result into when. So it has to be entered into the system. So if I ask a question, if there are 8 locations in the buffer, and the first instruction which is there in the buffer is not found the result, it is still false, that means this unit is still doing it, maybe as a div operation, it is still going on, all the results are ready, all of them are ready, but can I write these results into the register? No, because this is the first instruction came. I should wait till this instruction is executed, completed, and the value is available, and I should start writing into the register set in the same order. Now my question is, can I issue one more instruction? Because all of them are completed. If all of them are completed means all the functional units are free except maybe this functional unit. All of them are free because all of them have computed the instruction and they have put the results now. But I can't schedule one more instruction because my ROB depth is only this much. And the head top of the instruction ROB, I have an instruction which is not yet over. So all the functional units can take a 10 minutes break like you guys. Okay. So the result of the instruction is here. The destination where it is supposed to go is here. And the queue, this is the topmost entry in the queue. So if I ask you whether it is a LIFO or FIFO or whatever, instructions are entering in the order and they exit in FIFO order. First in, first out, they go out of the buffer. But the values written into this can happen in any order. There is no sequence. Any functional unit completing the instruction, they can come here, hey, this is the result, this is the register where it is supposed to go, bye bye, I am going to execute next instruction. It will go on, take the next instruction, start executing it. It is the job of ROB to commit them in the order in which they are supposed to be. I hope this is clear. This is very intuitive. Unless you spend some time imagining yourself, it's not possible for you to understand and answer the questions in the exam. Okay, so I will complete it and stop. The head of the queue is the instruction which would be committed next if it has completed the execution. Okay, whatever I explained, I am going to show you in the slides. When this instruction completes, that is the topmost head of the queue, instruction I, its result value is copied to its destination register and the instruction is then removed from ROB. So once you commit the value, you don't need to keep it in the ROB. It can be removed. It's like a temporary cyclic buffer. You should understand this behavior. The next instruction to be issued in the issue stage of the instruction pipeline then joins the reorder buffer at its tail. So I'm assuming that the whole buffer is full, then they will come to the tail. Tail can be, the buffer can be full or incomplete. I'm saying tail means don't assume that it is the end of the buffer. It could be in the middle. Only some 3 instructions are there. Any new instruction will be added to the tail, not to the head. And if the instruction at the head of the queue is not completed and the reorder buffer is full, then further issue of instructions is held up. That is, the pipeline stalls because there is no free space in ROB for one more entry. So one thing is clear, Unless I have an entry in the ROB, I can't issue to the functional unit. ROB should have a space. If it is full, sorry, bad luck, pipeline has to stop. The result value of any other instruction lower down in the ROB, suppose I is here, I plus K is some instruction below I. I is the topmost in ROB. Say value of I plus K can be used as an input operand for subsequent instruction in the ROB. Remember, it is very important to say in the ROB because an instruction execution can happen only if it is present in ROB, and if it wants an operand from the value which is stored in the previously completed instruction, okay, value is here in the ROB which is supposed to be written into some register R10. The next instruction wants that R10 as an operand. So don't think that this instruction will wait for this instruction to be flushed out of ROB. No, it will take it from here. That is the beauty. Otherwise, there is no use of having this ROB. You should think and then analyze it. It will take it from here. It is equivalent to taking from R10. It has not gone to the destination register, but I know that this value is the latest value of R10, which is in ROB. So the next instruction can proceed with the instruction execution by taking this value from ROB itself, not waiting for this to be committed into register set and reading from there. Remember, the instruction operands are not always read from the register set. They are either taken from the reservation station or they are taken from ROB. If they are not in these two locations, that means what? We are using some old value which was computed by some instruction earlier, which has been committed to register set. So it is available in register set. So I can read it from register set. So they are checked from these locations because these are the places where the recently executed instructions will have their results in. Register set may not exactly show the real state of the processor. So as far as the execution of the CPU is concerned, the out of order execution of the instructions in the CPU, they don't need to wait for the values to be written into register set. They can take it from the temporary buffers which are there. Either reservation station, which is a temporary register renaming, or it could take from ROB if it is not yet committed. So provided that instruction has been completed. See, you cannot take the value unless it is completed. So ready should be true. That means what? That instruction I plus K is completed and it has computed the value and it knows which register it is supposed to go and then says it is true. If it says true, I want this register value, maybe register 11, and then this is the value. Some instruction below wants add, I want some operand from R11. It is not committed yet because it is I plus K. That means it is not yet committed. That means I can take from here the operand. Where it will go? From ROB, it will go to the reservation station. Okay. Nowhere the register set is coming into play, though instruction says it is R11. R11 is the value in recent value, the latest value of R11 is not in R11. It is in the ROB right now. So I take it from here. Okay. I hope this is clear. If you don't get it, if you listen again, if you have patience and interest, forget about patience. If you really have interest to learn about architecture, you listen again. The techniques of operand forwarding is combined with the concept of ROB. So I told you in scoreboarding there is no forwarding. If you think it is similar to operand forwarding, which was in pipeline. There what was happening? It was the intermediate result before going into the register set, it was in the pipeline register. Now instead of going into the pipeline register, they are in ROB now. In ROB, multiple instructions which have been completed may have their results. which are not yet committed to the register set. So it is equivalent to operand forwarding, which we saw in pipelining. If you understand all of them together, I can assure you, you have learned architecture, processor architecture. So the value in ROB are simply work in progress. These values are not reflected in the program or processor state as needed for a context switch or for exception handling. So I told you this, I explained you already. These are all to enable the instruction execution. Okay. So write back of instructions are done in the original program order, where the results of the instructions are written into the destination registers. Okay. I hope these explanations add to what I have explained in the class now. So even if you read the PDF separately, and if you recall something what I told in the class, you don't need to go through the video again, unless you have some specific doubts, and then you can forward and backward. You can understand from this. That's why I am taking pain to write it. Otherwise, I could have just explained it there and then stopped there. Okay. I know the difficulties of students. I am doing everything possible. It's like this. Horse can be brought to the water to drink. I can only bring the horse to the water pond. I can't make it drink. The horse has to drink the water. If if the horse decides to starve and doesn't want to drink water, I can't do anything. I can only bring it. That is what I'm doing. It depends on whether you are interested in learning or not. So ROB holds up the execution of the dependent instruction if its input operands are not available. So what is happening is ROB also will not have all the results. Okay, I told you that some instruction, if it wants the operands from the ROB, you can take it. But if it is not available, what can I do? I cannot go to the register set. If it is not available here, it won't be available there. If suppose you see there and then you understand that it is some of the instruction which is in execution is supposed to produce the result. Okay, if it is supposed to produce the result and if it is not ready, I cannot go to the register set and take it, because this will be a stale value. So this instruction has to be stalled. Remember, if I am supposed to get it from the instruction which is in ROB, which is not a completed execution, I cannot go to the register set and take the value, which will be stale value, old value, because I am expecting one of the instructions here which has come prior to me to compute the value which I need it here as an operand. If I don't have it from ROB, it means that it is not yet over. I cannot proceed further. So that instruction has to be stalled. That means it will be waiting for the operand to be available. Operand forwarding from ROB could speed up the execution. Actually, you can speed up the execution. You don't have to wait for the write back. So these hazards, it can be addressed with the register renaming. So these hazards, we addressed it with the register renaming. I will not explain to you. You think about it, why it is helping. I already explained. I am not repeat it again. Control dependencies are not handled by ROB. What I mean by control dependencies, if there is a misprediction, okay, this bullet you may not understand it fully because I have not spoken about prediction and branch prediction and all that. So I will hold the discussion for maybe till tomorrow. Okay, misprediction and branch prediction I have not spoken about. Summary: it enables execution of ROB enables execution in the instruction in parallel if there are no dependencies. ROB as such does not resolve dependencies. Dependency handling is done by the unit before executing the instruction, not by ROB. ROB only maintains the record. Instruction issue and commit are in program order. Program and processor states are correctly preserved by committing it in order. It is a simpler technique to enable parallel execution along with preserving program order. So we are trying to improve parallelism in the hardware, at the same time preserving the program order. Precise exceptions can be achieved. I told you it can be achieved because you are committing to the register set in the order in which the program executed. So even if a division has a 0 divide by 0 exception, anything below is not committed. So what is the value in register set is still correct. precise exception is supported with the help of ROB. With this, I wanted to cover this also. I am sure you guys will kill me if I do that. Oh.